one final topic I want to cover about equilibrium constants and delta G before we move on to thinking about things besides gas phase reactions. What we're talking about here will apply to non-gas phase reactions, just like the Van 't Hoff equation, same thing, is how the difference between delta GR without the naught and delta GR with the naught, right? So we have this equation, delta GR is equal to delta GR naught plus RT natural log of QP. And what tells us whether a reaction is going to happen is this value, delta RG, right? How does G change with extent of reaction, dG d psi, right? That's what this is defined as. And so when this equals 0, the reaction will stop moving, right? Because there's no longer a change in Gibbs energy. If this is positive, the reaction will go in the reverse direction. If it's negative, it'll go in the forward direction, right? This value changes as the reaction happens. So delta G is not a constant. Whereas this delta GR naught, this is a constant value. And this is constant because it only considers one specific set of conditions, that is the standard conditions, where all the pressures are equal to 1 bar when we're thinking about a gas phase reaction. When we're thinking about condensed phases, there's some additional things there, like concentrations are all equal to their standard values of 1 molar and things like that. Or more accurately, they're equal to activity of 1. Anyway, so one way we can look at this is if we have delta GR, we can substitute. We know delta GR naught is equal to minus RT natural log of Kp, right? We can substitute that. This is just from the definitions. And then we'll have this plus RT natural log of Qp. And then we can go ahead and combine these equations and say that delta G for the reaction, the non-standard, is equal to RT natural log of Qp over Kp. So a reaction quotient divided by our equilibrium constant. Now, one thing that should be pretty obvious, if Qp is equal to Kp, then this term goes to 0 and delta G is equal to 0 and we're at equilibrium. And that's sort of our definition of the equilibrium constant, is that it's Q at equilibrium. So that makes sense. But what I want you to think about, I'd like you to pause the video and think about this. If Qp is greater than Kp, right? So if the reaction quotient is greater than the equilibrium constant, which direction will the reaction go? So I want you to pause the video and answer that question. Okay, so hopefully you thought about that and got an answer, and then we'll talk about this. Qp tells us which way a reaction is going to go. Is it going to proceed to products or reactants? And so if we have Qp greater than Kp, we'll have the natural log of a number greater than 1, which means that this will be a positive value. Delta GR will be positive, which means the reaction will proceed towards reactants. Right, reaction or goes to the left. Right, it proceeds towards the reactants, not the products. And the easiest way to think about this is if we remember, the definition of Qp is that we have our sort of our concentrations of our products on the top and concentration of reactants on the bottom. If Qp is bigger than Kp, that means we have this value on the top is larger than it needs to be for equilibrium. So we have to transfer some of our products to reactants to get the Qp value to be equal to Kp, which is what we want at equilibrium, which means that our reaction proceeds to the left. And if we have the opposite, right, if Qp is less than Kp, then we'll have delta G will be negative for our reaction, and the reaction will go to the left. Or, sorry, not to the left. The actual reaction will go to the right. Reaction goes to the right. So this is just a reminder that we often are looking at delta G naught values and calculating equilibrium constants, but that does not tell us which way a reaction will proceed at a single instant of time. For that, we need to calculate Q for that reaction, and then look at how Q compares to K. And using this logic here, we can decide, is this reaction going to proceed in a forward direction or a reverse direction based on which way you need to go to reach equilibrium. So this is just something I wanted to emphasize and re-emphasize that delta G and delta G naught are different things. Delta G naught is a constant and is a fundamental property of that reaction at a particular temperature, whereas delta G without the naught applies to your actual reaction that's not at standard conditions and tells you is your reaction at equilibrium, or does it need to move one way or the other to reach equilibrium.